is Luke. You can call me Lucky, and I'm going to race this river. And I'm gonna win. I need to go get it. How do I get back up? Oh, there was like a ramp here. Okay. Alright, now I realize this is a wildly absurd claim to make, so let's establish the rules of the race. I'm gonna ride this single speed bike a little over 10 kilometers from the countryside of Sawara Ward to Fukuoka's inner city. I'm gonna do all of this on a rainy day. Put a pin in that. I know it sounds random, but it's very important that I do this on a very rainy day. But let's talk about that later. I want to get inside. So we need to address some fundamental questions, like how do you even go about racing a river? When I was a kid, I used to play this game called Tigger's Honey Hunt, and there was a mini game titled Pooh Stick, which is a terrible name for anything, but the premise was simple. You and your opponent throw a stick into a river, and whoever's stick reaches the finish line first is the winner. Now, I thought about doing something similar with an air tag, but there are literally hundreds of places where a tracker can get bogged down, stuck, or lost entirely. So we need to take a more measured approach. Calculating the speed of a river is a good place to start, but now we have another problem. How do you figure out how fast a river is? And before you settle comfortably on your intuition, I want to pose to you a question. Look at these two rivers. Do you think I could beat River A? What about River B? I want you to think about that for a second. If your answers are yes and no, I have bad news for you. They're the same river, on the same day at slightly different locations. So clearly it's unfair to measure a river's speed at any one given point because rivers are dynamic systems. They vary in speed and size over scale and time. So in order to find the solution to this initial problem, we need to take a step back and take a look at the big picture. If I go any further, I'm gonna fall in. From a functional perspective, rivers are just a physical landscape feature which moves water from point A to point B. And rivers can be measured by their ability to move water into and out of their system. In fluviology, we call this discharge. And the discharge equation is so comically simple. It is literally discharge, represented as Q, is equal to area, where area is a perpendicular cross-section of the river multiplied by velocity. And that's it. Now, I'm quite proud of this picture that I've drawn, but I think there's a better way to visualize and understand this equation. So, please join me in the shower. This is a scale model which I built out of clay and a turf tile. And considering it's been like 2 decades since I've made anything out of clay, I'd like to say I did a pretty bang-up job. Though, I will say this took me a long time to make. How long exactly? Longer than I'm willing to admit. So, moving past that, imagine this is the top of the mountain and this is where the river feeds into a large body of water. If I turn on the water, you can see that a river emerges with that's the backwater bathtub. If I turn on the water, you can see a river emerge with a consistent flow and channel profile. We can estimate a quick and rough cross-section area with a ruler and some basic equations. And to measure speed, I've enlisted the help of this beautiful adventurer. This is the Shirase Maru. We're going to use the stick method and record the time it takes for this small boat to travel from a designated point A to point B. Finally, we're going to put it all together and solve for Q.
What shall we do with the drunken sailor? What shall we do with the drunken sailor? What shall we do with the drunken sailor? Early in the morning, way hey and up she rises, way hey and up she rises, way hey and up she rises, early in the morning. Put him in the longboat until he's sober, put him in the longboat until he's sober, put him in the longboat until he's sober, early in the morning. Way hey and up she rises, way hey and up she
Well, this has been educational and entertaining, but how do we use this information to race the river? Well, remember when I mentioned earlier that I'd have to race the river in the rain?
It's very important that I do this on a very rainy day.
Well, this is when I explain why. You see, when rain falls, it follows a sort of bell curve pattern, raising gradually and then peaking and then gradually receding. We can replicate this in the scale model with a spray bottle and a shower head. And while I do this, I'm going to chart the discharge over time. So this is light precipitation. It's starting to rain, starting to rain, starting to rain, getting heavier. Heavy rain, heavy rain, heavy rain. Whoa, the water's so powerful it's going upstream. Sorry, that was a bad idea. Gradual result. Gradually, gradually. Receding. And rainfall is over. Congratulations, you've discovered the hydrograph. A hydrograph is, in its simplest form, discharge over time. Put in other terms, it describes how quickly a river completes its purpose. But a river on a normal day has a straight hydrograph, meaning we can't really tell how quickly the river is doing its job. But on a rainy day, we can tell. Notice the congruency of the precipitation event and the hydrograph. This is no coincidence. These values are corollary. The hydrograph is literally the precipitation water going through the river system. We call the time between these two peaks the lag time. And it stands to reason, in my head at least, that if I can beat this time,
I will have beat this river in a race. And with that, let's take a break. Let's take a break. I have been cycling all over this countryside for like the past 3 hours trying to get good footage, but that's not the point I'm trying to make. Let's take a break today. In today's video, we discussed the theory of this experiment, essentially how we measure rivers. In the next video, we'll discuss the more practical aspects of this experiment. Essentially, I'm going to show you the scientific equipment I'm going to use to conduct this experiment/race. In essence, we're going to discuss methodology. Thank you for watching. I hope you learned something new today, and I'll see you in the next lesson. Take care. And also look how beautiful this view is. It's dragonfly season. They are everywhere.